For years, OpenAI released its flagship artificial intelligence as a single, centralized product. With the launch of the GPT-5.6 family, they have moved away from that structure, replacing it with a decoupled ecosystem. There is a second anomaly in this release. Days before the planned launch, the rollout timeline was altered following an access request from the United States government. This timeline outlines how the dual rollout occurred. On June 26, 2026, OpenAI shipped GPT 5.6 as a restricted preview available only to a set of vetted partners. Public availability did not follow until July 9th. This launch operates on two tracks: a shift in how the models are architected and priced, and a new framework for how the government interacts with frontier AI releases. Previous generations of GPT operated as one engine. Developers and end users routed their tasks through a single model, adjusting effort and parameters to scale the compute up or down based on the difficulty of the prompt. That system transitioned into three distinct tiers: Sol, Terra, and Luna. Sol replaces high compute reasoning models. Terra replaces balanced models, while Luna takes over high-speed background processing. Decoupling allows each tier to iterate on its own independent release schedule. Removing the centralized structure allows for asymmetrical capability scaling. This means smaller, highly efficient models can now evolve faster than the heavier tiers. To understand the economic differences between these tiers, we have to look at two metrics. The context window is the maximum amount of text the model can hold in its working memory at one time. Tokens are the fundamental units of text that the model actually reads and processes. This data matrix breaks down the intended market positioning across the family. Sol is designated for complex logic and reasoning. Terra handles general application tasks. Luna is built for high-volume, low-latency efficiency. Across all three models, OpenAI has split the pricing per million tokens into a precise ledger. Costs are strictly delineated between standard input, cached input, and generated output. Below the pricing, the matrix defines the numeric context window limits, alongside a hard cap on the maximum output tokens each model is permitted to generate in a single response. The models also separate by knowledge cutoff date, showing discrepancies in how recently the training data for each tier was finalized. Finally, the matrix defines the reasoning capability levels for each tier, placing a boundary on how much cognitive effort each specific model is allowed to expend. Developers face a mathematical trade-off. They must explicitly balance the cognitive depth required to solve a problem against the financial efficiency of executing it. This flowchart compares legacy processes to a new feature called programmatic tool calling. Instead of executing external tool calls in a slow, linear sequence, the 5.6 models write code to orchestrate multiple tool calls simultaneously. That capability feeds into a new beta multi-agent mode. Developers can now coordinate distinct subagents in parallel across different tasks and synthesize the results back through a central orchestrator. For the highest friction problems, the API introduces Pro Mode and a new max reasoning effort tier. These allocate extended compute resources, giving the model more capacity to work through complex logic before returning an answer. OpenAI also introduced explicit developer control over prompt caching. Rather than the system caching inputs automatically, developers choose what data to cache, introducing a new cache-write pricing dimension to the API. The 5.6 architecture allows reasoning state to persist across multiple conversation turns. Evaluators also report gains in front-end UI design quality and instruction following accuracy. Large language model compute is now more than a budget for text generation. It is an intricate ledger requiring developers to manage orchestration, state, and memory. This bar chart displays OpenAI's self-reported performance. The blue bars represent the gains the GPT 5.6 family claim across coding benchmarks, general intelligence indices, and evaluations in biology and the life sciences. However, data published by independent evaluators provides a counterpoint. The gray bars illustrate third-party verification, and in several categories, the independent figures do not reach the levels reported by OpenAI. On specific general intelligence tests, independent researchers concluded that the gains achieved by GPT 5.6 were marginal, with improvements falling within the bounds of statistical noise. This chart isolates 𝗬𝗍bench Pro, a highly scrutinized coding benchmark. On this test, a competing model scored significantly ahead of GPT-5.6 Following the independent publication of those numbers, OpenAI released a formal response criticizing the methodological integrity of the 𝗬𝗍bench evaluation itself. As models reach the frontier of current capability, self-reported figures are increasingly contested. Independent auditing remains the only way to verify actual technical advancement. This timeline illustrates how the June 26th preview operated. The initial rollout of GPT-5.6 was isolated exclusively to a set of vetted partners at the request of the US government. The intervention was triggered by OpenAI's own preparedness framework. Internal evaluations flagged elevated capabilities, specifically in biology and cybersecurity risk assessments. OpenAI complied with the request to delay wider release, but they publicly stated that government-gated access should not become the norm for the industry. This represents a significant moment in the industry. For the first time, frontier AI capabilities were assessed and restricted by the government before they were permitted to become a public-facing product. This cost flow graphic illustrates the mechanics of the prompt caching system. Developers pay a 1.25x cost multiplier on the standard input rate to write data into the cache block. Practically, developers are accepting a financial hit on the initial prompt. They pay that premium upfront in exchange for greater read efficiency and lower costs on all subsequent requests that hit the cache. Based on the pricing, the decision framework is rigid. SOL should only be deployed when a task mandates top-tier reasoning capabilities and the compute provided by Pro Mode. Terra serves as the default, providing a balance of cost and capability. Luna is for high-volume operations, where efficiency and lower pricing are the primary requirements. Success within the GPT-5.6 ecosystem requires precise architectural budgeting. Engineering an AI application today now relies just as much on financial planning as it does on prompting skill. The launch of GPT-5.6 leaves two defining legacies. It restructures how AI models are built and priced, and it formalizes a cycle of government involvement in the rollout of frontier technology. At the time of recording, broader geographical and platform availability for the entire 5.6 family was still expanding. The GPT 5.6 release marks a move away from the single all-purpose model, establishing a tiered architecture, and a new standard where national security reviews precede commercial availability.